In-depth analysis of trends. Behind the explosive demand for HDI PCBs, how do technological revolution and market opportunities resonate? Opening scene. Close-up of electronic component production line plus dynamic data charts. In the 2025 electronic manufacturing industry, high-density interconnect printed circuit boards, commonly known as HDI boards, are no longer an exclusive configuration for high-end equipment, but have become a solidly indispensable component. Data shows that the global HDI board market size has exceeded $12 billion, among which the HDI segment market in the AI and HPC server fields has a compound annual growth rate, CAGR, exceeding 32%, and is expected to reach $3.17 billion by 2028. This wave of growth is by no means accidental. It is an inevitable result driven by technological iteration, scenario expansion, and industrial upgrading. Today we will dismantle the growth code of HDI PCBs step by step from the aspects of demand drivers, technological breakthroughs, selection logic, and future layout, providing references for decision-makers in the industry. 3 core engines of demand explosion. The qualitative change from optional to necessary. The growth in demand for HDI PCBs is not driven by a single field but by a resonance effect formed by technological upgrades across multiple sectors. The core driving forces mainly lie in 3 directions. 1. AI computing power revolution. High-end HDI becomes a necessity for computing infrastructure. The explosion of computing power in AI servers has directly pushed the demand for high-specification HDI to its peak. Take the NVIDIA GB200 as an example. It adopts a 6th-order 24-layer HDI design, which is far more complex than traditional PC motherboards, and its manufacturing cost is about 3 times higher. Such high-multilayer HDI must achieve precision processing with a 3 mm, 0.0762 mm, line width and 0.15 mm aperture, while ensuring a signal delay error of less than 1 ps to support the high-speed interconnection of GPU clusters. The global market for PCBs with 18 layers or more is expected to grow by over 40% in 2025, with the Chinese market growing even faster at 67.5%. And HDI technology is the core support for achieving high layer counts and high density. 2. Terminal equipment upgrades. Mandatory requirements for miniaturization and integration nowadays. With the upgrading of consumer electronics and automotive electronics, HDI has transformed from a high-end option to an entry-level standard. For foldable screens and wearable devices, a 0.25 mm ultra-thin HDI motherboard can reduce the device weight by 30% while integrating 5G modules and multi-camera interfaces, and it has now become a standard configuration for flagship models. Looking at new energy vehicles, the 800V high-voltage BMS system requires a 10-layer thick copper plate, 6-ounce copper thickness, HDI board, which must also pass the high and low temperature cycle test from -40 degrees Celsius to 125 degrees Celsius to ensure reliability in high-voltage environments. In terms of medical equipment, implantable devices such as pacemakers adopt embedded component HDI technology, which can reduce solder joints by 50% and must pass biocompatibility certification to achieve both miniaturization and high reliability. 3. Communication technology iteration. Performance necessity in high-frequency scenarios. 5G base stations and millimeter wave devices have extremely strict requirements for signal integrity, making HDI the optimal solution. The through-hole design of traditional PCBs causes signal stub effects, while the blind and buried via technology of HDI can shorten the signal path. Combined with the process optimization of plus or minus 7% impedance control, it can significantly reduce the attenuation and reflection of high-frequency signals. In 5G AAU equipment, composite substrates integrating high-frequency materials and HDI technology have become the core carrier for realizing millimeter wave communication above 77 GHz. 2. Technological breakthroughs. Solving the 3 core challenges in HDI manufacturing. Demand drives technological upgrading. The large-scale application of HDI PCBs is largely due to the breakthroughs in 3 key processes, which are also the core indicators distinguishing manufacturers' technical capabilities. 1. Microvia processing and whole metallization. The foundation for density improvement. The core advantage of HDI lies in microvia technology. Laser drilling has replaced traditional mechanical drilling, achieving a qualitative leap. The aperture has been reduced from 0.2 mm to 0.05 to 0.1 mm, and the precision has been improved by more than 4 times. The breakthrough in whole metallization technology has solved the problem of interconnection reliability. For example, horizontal electroless copper plating technology can form a uniform copper layer on the whole wall, ensuring the conductivity and overall machine reliability of high-multilayer HDI such as AI servers. At present, domestic enterprises have achieved independent breakthroughs and import substitution of this technology. Point 2. Compatibility of large size and high density. Expanding application boundaries. The once technological forbidden zone of large-size HDI has now achieved breakthroughs. By selecting high-TG substrates, such as FR4 high-TG, adopting symmetric lamination design, and applying vacuum lamination technology, the warpage of 800 mm x 600 mm large-size HDI boards can be controlled within 0.7% while maintaining a 3 mm line width precision. The application of such products in the photovoltaic inverter field can reduce the equipment volume by 30% and improve heat dissipation efficiency by 25%, directly opening up a blue ocean market for HDI. Point 3. Intelligent quality control. Balancing yield rate and cost. The high-precision requirements of HDI manufacturing are prone to low yield rates, and the intelligent production system has provided a solution. Through full process AOI, automatic optical inspection, big data traceability systems, and AI algorithm optimization of production parameters, leading enterprises have increased the HDI yield rate to 99.9%, while achieving 24-hour prototyping and 48-hour small batch delivery, compressing the R&D cycle by 50%. 3. Selection decision guide. Precise adaptation logic between HDI and traditional PCBs. Faced with the growth in HDI demand, the most difficult decision for enterprises is whether to use HDI and which type of HDI to choose. Next, we will clarify the ideas through technical comparisons and scenario adaptation. First, let's look at the core differences between traditional PCBs and HDI. In terms of line width and spacing, traditional PCBs are generally 150 to 200 micrometers, 3/3 mm, while HDI can reach less than or equal to 100 micrometers, even 1/1 mm. In terms of interlayer interconnection methods, traditional PCBs mainly rely on through-holes, which take up a lot of space. HDI uses blind and buried via stacking, which can increase the wiring density by 300%. In terms of substrate characteristics, traditional PCBs are mainly FR4 with a dielectric constant of 4.2 to 4.8, while HDI uses high-frequency low-loss materials with a dielectric constant of 2.2 to 3.8. The reliability test standards are also different. Traditional PCBs undergo 500 thermal cycles with an impedance of plus or minus 10%, while HDI undergoes 1000 thermal cycles with an impedance of plus or minus 3%-5%. In terms of application scenarios, traditional PCBs are mostly used in home appliances, lighting, and basic industrial equipment, while HDI is used in fields such as AI servers, 5G equipment, and high-end consumer electronics. Let's talk about scenario adaptation. There are 3 types of scenarios where traditional PCBs are preferred. First, industrial. Control motherboards with an operating frequency of less than 1 GHz. Second, non-precision components such as power modules and LED lighting driver boards. Third, household appliances that are cost-sensitive and have no miniaturization needs. There are 4 types of scenarios where HDI PCBs must be used. First, size-constrained portable devices, such as those with a motherboard thickness of less than or equal to 0.6 millimeters. Second, high-frequency communication equipment, such as 5G base stations and millimeter-wave radars. Third, equipment with high reliability requirements, such as automotive ADAS systems and medical implantable devices. Fourth, high-multilayer designs with 12 layers or more that also need to control weight. Finally, let's discuss the key factors for cost control. Although the cost of HDI is higher than that of traditional PCBs, it can be optimized through reasonable design. First, the selection of order. Most consumer electronics can meet the demand with 1 to 2 order HDI, and there is no need to blindly pursue designs above 3 orders. Second, process matching. Choose chemical silver immersion surface treatment for ordinary scenarios, and electroplated nickel gold for high-frequency scenarios. Third, manufacturer selection. Prioritize manufacturers with large-scale production capabilities, as their yield advantages can reduce unit costs. 4. Future trends. 3 core competitive focuses of HDI PCBs. The growth in HDI demand is not only a quantitative expansion but also a restructuring of technology and market patterns. Future competition will focus on 3 directions. 1. Accelerated technological stratification and domestic substitution. China's PCB output value already accounts for 56% of the global total, but high-end HDI previously relied on imports. Now the situation has changed. Leading enterprises have achieved breakthroughs in the AI server and automotive electronics fields by cooperating with customers such as Huawei and NVIDIA. Technologies such as horizontal electroless copper plating and large-size HDI have reached the international advanced level. In the future, the industry will shift from low-end involution to high-end stratification, and enterprises capable of producing high-order HDI, above 4 orders, and high-frequency composite boards will occupy a dominant position. 2. Dual driver of greenization and intelligence. Environmental protection policies have now become a hard indicator for industry access. Green processes that adopt lead-free solder, water-based solder masking, and achieve a waste liquid recovery rate of 90% will become one of the core competitiveness of enterprises. At the same time, the application of AI in production will be further deepened, covering the entire process from parameter optimization to design simulation and fault prediction, promoting HDI manufacturing towards zero defects. 3. Heterogeneous integration and technological convergence. With the development of chiplet technology, the boundary between HDI and packaging substrates is becoming increasingly blurred. Composite technologies such as embedded components, rigid flex combination, and TGV through glass via have become new directions. For example, in space equipment, substrates integrating nanocoatings and HDI have achieved the dual goals of low loss and high reliability, which also means that the application boundaries of HDI will continue to expand. Conclusion. Core actions to seize the HDI growth dividend. The growth in demand for HDI PCBs is not a short-term trend but an inevitable result of the electronic industry's upgrading towards precision and high performance. For enterprises to seize this dividend, they need to do 3 things well. First, clarify whether to use HDI through scenario and technology matching. Second, select suppliers with core technologies, such as laser drilling and hole metallization, and intelligent quality control capabilities. Third, lay out emerging HDI fields such as high frequency and large size and advanced, and this technology-driven industrial transformation. Only by transforming demand insights into precise technical selection and supply chain layout can enterprises take the initiative in the wave of HDI growth.